Всем привет, меня зовут Timur Doumler. Мне сегодня выпала честь открывать эту конференцию. Как вы слышите, я владею русским языком, так что вы можете со мной на нем общаться. Но вот доклад я буду делать на английском, мне так удобнее, привычнее. Я надеюсь, что все равно будет понятно. So with that, I will switch to English, and let's start the talk. We're going to talk about C++20, speaking about bringing the future into today. This is exactly what we're going to do. So this is the timeline of the C++20 kind of release cycle. So there's a new standard every 3 years. The C++ standard committee has a meeting 3 times a year, which means it gives us 9 meetings to finish a new standard, new C++20 standard. So these are the 9 meetings. And the first time I gave a version of this talk was in June, I think, in St. Petersburg, which was there, before the Cologne meeting. And that was officially the feature. You see it says here, feature complete. So then I thought, well, we know what C++20 is going to look like. So I gave this talk, and then we had a meeting afterwards in Cologne in July, and stuff has changed quite significantly. So, well, so the next time I gave a version of this talk was at CBPCon, which was here after the Cologne meeting. And then I thought, okay, well, stuff has happened. Probably now we're going to know what C++20 is going to look like. But then again, we had a meeting in Belfast just a few weeks ago. And again, stuff has changed, right? So now we are here. And I think this is like the ultimate version of this talk, because now we actually know what C++20 is going to look like. Because we only have 1 meeting left in Prague, which is going to be in February. And this is basically just to fix a few very, very last-minute bug fixes. And that's it. And then after that, we're going to ship the new C++20 standard. So that's going to happen very, very soon. I'm super excited about this. I hope you are as well. And let's talk about some of the stuff in that new standard today. So this talk. The C++20 standard contains 2 parts. There's a language part and a library part, okay? And typically, the first third is the language bit, and the last 2/3 are the library bit. And today, we're not going to talk about any of the library stuff, okay? We are going to just talk about language features. So C++20 is a very big release, so it's the biggest update to the language since C++11. So what's in there? There's quite a lot of features. There's a few big ones. There's concepts. There's modules. There's no contracts, actually. That has been removed at the last minute. I'm not going to talk about that now. Quite an interesting story. If you want, you can ask me at the bar later. I'm happy to share some stories about contracts. So we don't get contracts, but we do get concepts, modules, coroutines, and we also get the so-called spaceship operator, or the consistent comparison. So these are quite big features. And today, we're not going to talk about any of these either in this talk. We're only going to talk about the rest. Okay, all these like little small features, little small additions that might slip through the cracks if you only look at the big ones, but are actually super useful and are making code cleaner, better, easier to write, and gives you a lot of really nice tools. So I'm going to talk about this stuff, and I tried to kind of structure this a little bit in this talk. So I have 6 sections here. We're going to start off with initialization. Then we're going to talk a little bit about structured bindings, which is a feature from C++17, but it's been improved in C++20. Same with Lambdas. They've been around since C++11, but then they got better in 14, they got better in 17, and they get better again in 20. And we're going to talk about templates. We're going to talk about Const Expert and compile time programming. And at the end, if we have time, maybe a few miscellaneous other bits. So let's start with initialization, right? So I'm not sure if some of you have seen my talk about initialization in C++, which I did some time ago. So let's just start where we left in that talk. Let's start with aggregates. A lot of work has gone into aggregates in C++20. Aggregates are useful. Aggregates are these simple types, which basically only have a bunch of members and not much else. And if you have an aggregate, you can aggregate initialize it, right? So you can do something like this. This was possible since C and C++98. Now in C++20, we get a new way of doing this, which is called designated initializers. So you can do this. So you can actually explicitly say which members you want to initialize. And this is the feature that has been in C since C99. So now we get this feature finally in C++ as well. There's slight differences between C and C++. So the way it works in C99, you can also define these things out of order. So you could say .c equals 7 and then .a equals 3. So you can flip the order. You cannot do this in C++ because in C++ we have constructors and destructors, right? So the order matters. You initialize members in order of declaration. You destroy them in the reverse order. So you can't order matters in C++. But you can omit things in the middle, you can omit things in the beginning and the end. And as with regular aggregate initialization, if you don't initialize a member, it's going to be 0 initialized, right? So it's also safe, nice, you never end up with like uninitialized integers or something like that. The other thing you cannot do in C++, you can't nest them, you can't write .c.e, but you can write .c brace.e, so that's fine. You cannot mix designated initializers with regular initializers, because why would you ever do that? But okay, in C you can. And you can't use it with arrays. But otherwise, pretty much, we get this C99 feature in C++20, which I think is cool, it's exciting. And actually, speaking of aggregates, we changed the definition of what an aggregate is. And that's a very, very tiny change in the standard, which was really, really hard to convince the committee to do because it was a breaking change. So in C++17, an aggregate is an array or a class with no user-provided explicit or inherited constructors. In C++20, an aggregate is a class with no user-declared or inherited constructors. And that fixes a weird hole in the kind of language where aggregates were previously able to declare constructors as long as you don't define them. And that was really, really weird. So in C++17, you could write a class like this, right? You have an aggregate and you delete the default constructor, okay? You're saying you should not be able to initialize this class. You should not be able to create one of these objects. This is what I'm saying here, okay? So if you try to do that, you get an error, well, the default constructor is deleted, okay? Nothing surprising. But in C++17, you could just add brace. And that would be okay, because now you're not calling the deleted constructor. Now you're doing aggregate initialization. And that's super weird, because you could kind of bypass the constructor interface that you have declared and do aggregate initialization instead. And people are usually surprised by this. I was certainly very surprised when I saw that this is possible. I was like, what? Like, most people who write these classes, they don't know this stuff, because like, people can initialize their objects, even though the intent was that you shouldn't be able to. So in C++20, we fix that hole. We say if you declare a constructor with, for example, you write it and you say equals delete, that's not an aggregate anymore. So then that will be an error in C++20. So now we have a cleaner separation between aggregates, which have no declared constructors at all, and non-aggregates, which can have declared constructors. And you can never have this mix-up. Am I using constructors? Am I using aggregate initialization? Am I bypassing the constructors and doing this other thing? No. It's very clean, much easier. There's a few other problems with aggregate initialization in C++ 11, 14, 17. So one of them is that aggregate initialization just doesn't work with macros. So for example, assert is a macro, right? So you can have an expression like this with a constructor that takes 2 arguments inside a macro. But if you use braces, that doesn't compile, okay? Because the preprocessor has a special rule. If you have a like an argument list in parens, and there's a comma in between, the parser knows how to parse it. But there's no such special rule for braces. So then the preprocessor thinks, if it sees this comma, well, that's the start of the next preprocessor macro, right? And then the preprocessor macro argument. And then everything just breaks because the syntax is just wrong. So that's unfortunate. And the actually bigger problem with brace initialization is that, or aggregate initialization, is it doesn't really work with templates, right? So you want to do things like perfect forwarding, because you want things like make unique and in place and other things. You want them to work, right? With aggregates. You want to be able to pass in the arguments to construct an aggregate to make unique or in place. It just doesn't work. And braces just behave weirdly in templates. So we fixed that in C++20. Now this will work, because now you can aggregate initialize with parens instead of braces, okay? So if you have an aggregate type. Previously, you had to use braces or equals braces. Now you can just use parens, and that's also going to work. And that's also going to work with arrays as well. So you can initialize arrays like this now. So this is really cool. So you know how in C++11 the committee introduced uniform initialization with braces? It kind of solved the problem, but kind of created a few other problems, and it's kind of, you know, some of those we mentioned. So now in C++20 with parens, we have, I think, a much cleaner way to actually have uniform initialization. I would call it uniform initialization to 0, maybe. So we don't really need braces anymore, right? Braces are weird. I don't know if you've seen some of my other talks, and you have, depending on, you know, you initialize a vector with 2 ints, and depending on whether you use braces or parens, like different things happen or whatever. So now in C++20, braces and parens will do the same thing most of the time, okay? So whether you have an aggregate, or you want to call a constructor, or you just want to initialize an integer, doesn't matter. You can use parens. It's going to be fine, except parens are not going to call initializer list constructors, okay? So if you want to do this like special thing where you want to construct a vector or some other container using the initializer list thing, then you can use braces, because that's the only syntax that's going to work for that. But then you're making it explicit, right? And the other thing is that braces don't allow narrowing conversions, right? So if it expects, you know, an int and you give it a float and that value doesn't fit into the int, then you're going to get a compiler error. So if you want narrowing conversions to not be allowed, and if you want to explicitly call initializer list constructors, you can use braces. For everything else, you can now use parens, and it will just work. Except, obviously, we still have the vexing pass problem, but then you can write auto, and then you can write the initializer on the right, and then that's also fine. So basically, I think now we have a very clean way of initializing things in C++20. All right. Not done with initialization yet. There's one more. So there is this really weird thing here. So let's say we have a struct, okay? Color. So this is something from a framework that I actually used to work on a few years ago. And I've been actually bitten by this specific problem quite a few times, and I'm sure many of you have as well. All right, we have this color class. You initialize it with, you know, RGB values, okay? Now we have a static, like global instance, right? So we have a color red, right, in some namespace, which is now static storage duration. We initialize it with some values. Okay, what's the potential problem here? So this is what we call dynamic initialization. Okay, so this means, because it's static storage duration, it means that this object will be initialized at runtime before main runs, right? So your program starts up, and then all the static objects are being initialized, and then main runs, okay? Is there a problem with this? Yes?
It doesn't work compile time. It's not accessible in Const Expert.
That's one problem, we get to that, but a more immediate problem. The order, yes. So we get this thing that we call the initialization order fiasco, where if one of these objects depends on another, the order in which they're initialized is not defined. And that actually happens. If you have another color which depends on red, or you have like background, or you want to like create a static rectangle, and then the color of that thing is red, then it's not guaranteed that this object will exist when you initialize the other one. So your program is just going to crash at startup, okay? How do you fix this? Okay, as you said, you want this to happen at compile time, right? So what you do is you put Const Expert on all the things, right? That's what we do in C++. So you put a Const Expert on the constructor, which means now it's a literal type. You can construct it at compile time, great. So then your color red, you also say it's a Const Expert object, so that's going to be now initialized at compile time. We call this constant initialization. So now it's guaranteed to happen at compile time. It's all safe. It's all fine. You solved the problem. Except there's one problem with Const Expert. It implies that it's const. Okay? So with this, color red is OK, right? You don't want, this is const, obviously. Color red is color red. It's not going to change. But if you have something like a background color, maybe you want to change it later, OK? So you want to initialize it, you want it to be there, but you want it to change it later. And that's not going to work with ConstantExpert because ConstantExpert implies const, so you can't modify it. So that's not going to work. So you're back into this. And then even if you have a ConstantExpert constructor, right? The problem with ConstantExpert is it might run at compile time, it might run at runtime. That's actually, like for me, that was really confusing when I first saw ConstantExpert, like in C++ 11. I thought this is like compile time stuff, but it's not. It might be compile time stuff, but it might be runtime, right? Depends what you give it. So here, if get background color itself is ConstantExpert, then you're safe. If get background color is not ConstantExpert, then it's going to compile, but it's going to initialize it at runtime, and then you're back at this problem, and you don't really know what it is. You have to look at the right-hand side. What you really want, you want to say, no, I want to initialize this at compile time. Okay? I want this to be safe, but I don't want it to be const. And we have a new keyword for that. It's called const init. So const init basically says, this has to be initialized, constant initialized, or initialized at compile time. Otherwise, it's not going to compile, but it does not imply const. So that's the difference to ConstantExpert, right? So this only compiles if get background color is ConstantExpert, so it's safe, but you can still modify get background color afterwards. Okay? So that's a new keyword. One more initializer-related thing. You know how in C++ we have if with initializer and switch with initializer? So in C++ 20, we're getting range-based for with initializer, and that's really cool. It gets rid of the particular problem. So let's say we have a database, okay? And then a database, you can get the users of that database. And then maybe the get users method returns a reference to something inside the database, okay? And then you write this for loop, right? For user in get database and then .get users. Does anyone see a problem with this? Yeah, I do.
Users are lifetime extended.
Well, except they're not. In a range-based for loop, that's not happening, right? So it might be UB. If get database returns a temporary, and then get users returns a reference into it, then after you've evaluated this expression, get database, lifetime ends, range-based for does not extend the lifetime of the temporary, and then it's a dangling reference and it's UB. Okay? So that's not good. So how do we fix this? In C++ 17, okay, well, you create the database before, right? You give it a name, then it's going to be around. But now this is not good because you pollute the outer scope, right? So that now it kind of leaks out of the loop. You just want it to be inside the loop. So then you would have to add braces around it to limit the scope, and then it becomes really verbose and long. So in C++ 20, you can just do this, okay? And this is very consistent with if and switch and all the others. So this is, you can initialize it, semicolon, and then do the range-based for thing. So that's nice. All right, so that's all I have on initialization. Let's move on. Structured bindings. So structured bindings have been around since C++ 17. I find them actually really, really useful. So if someone doesn't know what they are, it's this syntax with the square braces where you say, all right, so I have basically a class that consists of several parts, like members, or you have maybe an array that works as well, or a tuple or a pair. And then you initialize an object of that type, but instead of giving a name to the whole object, you give a name to the parts of the object. Okay, so here we have a widget object, but the object itself doesn't have a name, but you give a name to the bits, like the A, not the bits, the parts, A and B. So the first integer will be A, and the bool will be the B. And that's really nice because it saves you a lot of typing, right? You don't have to say auto widget equals blah, 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 and then everywhere you would have to do widget.a, widget.b, so that's a lot of code, so this is faster. The problem is that these are not really variables, right? These are just names for the parts of a variable, of an object. So they behave slightly differently from normal variables, these structure bindings A and B. So in C++ 17, there's a lot of stuff that you cannot do with them. In C++ 20, you can do more with them. So for example, in 17, you can't declare them as static, you can't declare them as thread local. In 20, this is all fine. And another one is a bit more interesting, is in C++ 17, you cannot capture structured bindings in a lambda, okay? So if you try to do that in C++17, it's going to say, well, A is not a variable, so you can't capture it in the lambda because it's a structured binding, right? That's weird. So in C++20, this is going to work. So this is good. Question though. Oh, actually there is a question here.
What about the rule? Will it work? Because currently we can't return part of object.
What about return?
Yeah.
Whether we can return a structure binding?
For example, we have this function get widget. And
Yes.
it's a function which returns this widget. Then if I return widget, then a real will happen. But now I decided I need only first part of it, for example, A.
Yes.
In that case, if I will try to return only A, then a real will not happen because it's a part of object that should be remained in the function, so it will be copied.
Yes.
Will this change will
Excuse me.
a real happen or not?
This is unrelated to that.
Okay, sounds
But there is a somewhat related question. What should this capture do, right? So should it, so I'm capturing by copy here. So should it copy just the A, or should it copy the whole object? Just A. So there was actually some discussion in the committee about this, because A is not really not an object. You have like the whole object, so maybe we should copy the whole object, but that would be really weird. So thankfully the committee decided that it should do what everyone expects it to do and just to copy A. And that's exactly what's going to happen. So that's also great. Speaking about lambdas, let's speak more about lambdas, because lambdas got a lot more awesome in C++20. So one thing you can now do in 20 is you can do a pack expansion, which is really cool, because you can now, if you want to forward a pack in a lambda into a lambda, you can just initialize it in the lambda initializer. And then there's more cool stuff. So lambdas are now allowed in unevaluated context. We're going to speak about this in a minute. And then lambdas without captures, so lambdas that don't have state, basically, and don't have like members inside, you can now default construct them and assign them, okay? And that's really cool. So first of all, unevaluated context, for example, decal type, right? So now you can put lambda in a decal type, and it's going to give you like a lambda expression in a decal type, and it's going to give you that type. You would think, okay, I mean, we could do before auto L equals expression, then decal type L, right? So how? But this allows you to just declare a lambda like this, okay? You might say, okay, this is still useless because we can just do auto F equals, you know, bracket, bracket, brace, brace. But auto, you cannot use auto for class members, right? But if you can do this, that allows you something that has not been possible before. You can have a member, class member of lambda type, like this, okay? This is cool. Why would you do this? Well, you might want to template this class on a particular type of function, like maybe some kind of callback, right? It's very, very frequent. And then sometimes you just want to store like a std function in there, but sometimes you don't, because you don't want to pay for the overhead. You just want to have any callable object, you want to template on that, and you want to store an object, you have a member of that type. And that makes this possible. And this comes up again and again. Whenever you have any kind of callback or function-like thing that you want to pass into the type. And that comes up in the STL, for example. You have something like unique pointer, which has a deleter, right? So now what you can do is you can just specify the deleter as a lambda just in the type, okay? And now you can just create these pointers, and you don't have to give it instances of that lambda over and over again. It's just part of the type. And you can just put the lambda directly in there. Same with sets. Like a set has a comparison function, and you can just do it like this. There's a question here?
What happens if we call the set to lambda, which is default constructed?
What happens if we call a default constructed lambda? Well, you call it. So the compiler knows how to construct these things. That's That's kind of the thing here. You just specify the type, and you can construct multiple instances of the same lambda type.
Is the empty function
Well, it's not an empty function. It's doing stuff here.
no, it's not previous slide.
Oh, well, this is just a toy example. This is an empty function. Yeah, just because it. Yeah, imagine there's some stuff in here. Then it's more interesting.
Can we check if it's empty?
Can we check if a lambda body is empty at runtime? I don't know. I don't think so. I don't know a way to do that. No. You can check that it takes no arguments and has no return type and things like that. But
Like it's empty function if it's not if it's default constructed, you can convert it to full.
that's different. So if you default construct a set function, it has no function. It is not associated with an actual function. So then calling it is UB. That's different from a function that does nothing. Those are two different things. I'm not sure we have time for all these questions now. I have quite a lot of slides to go through. So if it's not quick, then let's do questions at the end. Is that all right? Okay. Just remember the slide number, and we can come back to it at the end if we have time. Right, so you can do this stuff. More stuff you can do with lambdas is, so we used to have, we already have in C++ 14, they were introduced, generic lambdas, right? So you can write auto for the parameter type, and then it turns it into a template. Or like the operator paren is going to be a template. Now, as a kind of consequence of concepts, we're not going to talk about concepts here, but as a consequence of concepts, as a feature, we now have generic functions as well, right? So with concepts, you can do concept auto A, but you can also just remove the concept, and then it's an unconstrained templated parameter. So now you can write this, which has been around as a GCC extension for a while, but has not really been part of C++, and now it is. So we can just write not just an auto return type for a function, but also an auto parameter. And this is a template. This is a function template, right? This is really cool. I think this syntax is really nice, short. So that's good. On the other hand, sometimes you might not want to use this, right? Because maybe this type here, maybe you want to be able to name it. For generic functions, this has always been possible because you can just write the long syntax, right? You can just write template type empty and then my function, and then it takes a t or like a vector of t, but then you still have the t, the access to this type. Maybe you want to create a t and then push it back into the vector of t's inside that function. So you can do this because you can name this t, and for lambdas it has not been possible before because generic lambda is just auto, but what's this auto? I mean, you can do decal type of this thing, and then you can get the parameter type, but you can't unpack it like here, like vector of t, and then get the t. In C++ 20, you can write this. You can just take a lambda and add template parameter list, and that's going to work. So this is cool. I think the only thing missing now to make lambdas and functions syntax perfectly consistent is that you can write this short form also for freestanding functions, which is not in C++ 20, but you might get it in C++ 23, maybe. Let's see. So yeah, you can do more stuff with functions and lambdas. I think that's exciting, makes it more consistent. Now we're talking about templates here, right? So let's keep talking about templates. Templates, so there's one really exciting thing which just happened in Belfast at the last committee meeting. Just a couple of weeks ago, so this is brand new stuff. And I think this is like the last really big change to C++ 20 that we did before it ships, in a few months. So let's talk about non-type template parameters. So in C++ 98, 11, 14, 17, non-type template parameters really. So non-type template parameters, right? I hope everyone knows what that is. Really could only be integers or things that you can treat as integers, like pointers or enums, which is limiting. So in C++ 20, in the previous version, we had a new mechanism of doing class types as non-type template parameters, which was based on the kind of spaceship operator. And then, so it was a bit of a long story. I'm not going to go into the details, but basically what we ended up with was then if you have like an operator equals, and then you default it, then the compiler knows how to compare it, and then it was kind of weird, and we got basically a bug report saying this is kind of broken. And then at the last meeting in Belfast, we were trying to fix this. And we fixed this by completely redesigning how this works in a way that I think is a lot better and a lot cleaner and a lot more powerful. So one first piece of news or consequence of this design is that now you can use floats and doubles as non-type template parameters. That's really cool. So I don't know if some of you do kind of numeric stuff, but I'm doing audio and music software, and for that, basically, you need to compute lots of floats. Basically, an audio signal is just an array of floats, right? So what you want to do is you want to have lookup tables for these things, and you want to compute them at compile time, or maybe you have some float coefficients for some equations that you need to do over and over again, and you want to template some kind of thing on that. So being able to put floats and doubles into non-type template parameters and template on values of floating point type is really, really cool. So now I can do this, right? I can create a std array of doubles at compile time and put values in it at compile time and template on those values, okay? But it gets even better. So the way non-type template parameters work in C++20 is that we basically introduced this concept of a structural type. And the rule basically says you can use any type as a non-type template parameter, which is a structural type. What does that mean? So it means basically integers and floats, like all these fundamental numeric types, scalar types, are structural types. But also, every type where all the members are public and structural types is also itself a structural type, okay? So if you have a struct with two doubles in it, you know, a double is a structural type, and you have two doubles as members, and they're both public, which means this class, the coefficients, is also a structural type, which means you can also use it as a non-type template parameter. So you can do this. So you can template on the value of this object at compile time. Yes?
Why fields should be public? Why standard layout is not enough?
Why standard layout is not enough? Good question. Yeah, let's look at the paper after the talk. I think there's quite a lot of rationale in there. Right. So, moving on. Yes, so this is really useful because now, for example, if you have a filter which needs coefficients, like a polynomial, whatever, and then you want to compute like all these things at compile time, you can create a filter like this, and you can just give it a bunch of floating point values, and it's going to do whatever it does. So that's really useful to construct these pre-compute things at compile time. Right, templates. Another feature is class template argument deduction, or CTAD, which is another one of those features that has been introduced in C++17. For those of you who don't know what CTAD is, basically it lets you omit the template arguments of a class, and then it's going to deduce what the template arguments are from the initializer. So if you want to create a vector of int, you don't have to write the int, you just give it an initializer list of ints, and it's going to figure out that it's an int. So that's good. It also works with tuples, so we don't need make pair and make tuple anymore. You can just write std tuple, and it's going to deduce the tuple of what it is from the initializer. So it's going to figure out it's a tuple of input double bool. It's really good. It saves you a lot of typing, because sometimes these type names are really, really long, right? So if you have a scoped block, you might have a scoped block of std timed recursive mutex, and you don't want to type that every time, so you don't have to. But this feature was a bit incomplete in C++17. So C++20 adds CTAD for aggregates and CTAD for alias templates. So C++17 is kind of weird. If you have an aggregate type, like this, which just has 2 members in it. You want this to work, right? But unfortunately, it doesn't, because CTAD looks at constructors, and aggregate type doesn't have constructors, so it says, well, I don't have any deduction candidates. So in C++ 17, we had to teach that if you have an aggregate type, you always have to write an explicit deduction guide, which is just noise, right? You say, okay, if you see a pair of T and U being constructed with a T and U, deduce a pair of T and U. Like, it should be obvious, right? So the compiler should be able to generate this for you, and in C++ 20 it does, so you don't have to type that. This deduction guide is going to be automatically generated for you. There's quite a few cool patterns that you can do with this. For example, this is something that you can find this on CPP reference somewhere. It's a really cool trick where basically you have this kind of variadic template that inherits from a bunch of classes. And then you have to write this deduction guide in C++ 17. So that's an aggregate, right? Because the base classes of an aggregate are the aggregate elements. So the elements in our aggregate are the base types and then the members. So this is an aggregate. And then you can do this kind of stuff where you can just give it a bunch of lambdas and it's going to inherit from those. And basically it's creating an overload set. And then if you call this here, then it's going to automatically call the correct overload, which is this here. So this is really cool. But in C++ 17, you have to write this really annoying deduction guide. But because this is an aggregate in C++ 20, it's going to be synthesized for you. So this cool like overload set pattern becomes a lot easier to type. The other thing is CTAD for template aliases. So this is another thing that's kind of annoying in C++ 17. Like if you have a template alias like PMR vector, so vector of int works. You can just write vector v, but PMR vector doesn't work. You have to write vector PMR vector int because CTAD will not work for alias templates. In C++ 20, it does. So again, saves you a lot of typing, super useful. Right, so let's talk about ConstExpert and compile time programming. ConstExpert has an interesting history. So ConstExpert was introduced in C++ 11, and in C++ 11, it was kind of, you couldn't do much with it. So the feature was there, the compiler kind of, the basic kind of technology was added, but ConstExpert functions were very limited. They could only have a single return statement with an expression and pretty much nothing else. In C++ 14, it got better. There were more things you could do in there. You weren't restricted to a single return type anymore. You could actually write code in there. In C++ 17, ConstExpert functions again became more powerful. You could do more stuff in there. In C++ 20, again, they're getting a lot more powerful. So in C++ 20, in the ConstExpert function now, you can have all these things. You can have a try block. You can have assembly code as long as you don't actually evaluate that. You can use unions. You can use virtual functions. As long as the compiler can at compile time figure out what actual type the thing is, it can call the correct virtual function and you can do polymorphism at compile time. So then you also get dynamic cast and type ID, and you can actually use new and delete as well. It's not like new and delete at runtime. It's like special, right? So it's like compile time, but it works. And that really unlocks a lot of stuff. So now you can implement std vector and std string as Const Expert, which we are also getting in C++ 20. So this is really cool because now pretty much most of C++ you can now do at compile time. You can just write code and make it Const Expert. There's a few things that you can still not do in a Const Expert function, like you can't have a goto, and you can't have a reinterpret cast, and you can't throw an exception. So basically, this is like you get the sane subset of C++, basically, and you can use that at compile time now. So this is a huge topic. Obviously, I could just talk for an hour just about this stuff, and I'm not the expert in this. So I would just recommend you watch some talks from the actual experts who have worked on these features. So let me just point out 2 particular talks. David van der Voorde's keynote from this year from CSS Now, and Louis Dion's talk at CPPCon from last year, where these guys go into a lot more detail about why it's so cool to be able to do all these things at compile time now. I'm just going to quickly talk about one little thing that you can do at compile time. So here's the thing, running code at compile time, right? So this is a runtime function. You can turn it into a compile time function, okay? But it's not really, right? So it's Const Expert. So as I said before, if you give it a compile time constant, it's going to run at compile time. If you give it a runtime variable, it's going to run at runtime. You don't really know, right? Sometimes you want a function to only be to only run at compile time. Do you have a question?
Actually, the first time is maybe compile time.
The first time is maybe compile time. The second one is definitely not compile time. But sometimes you want to use these stuff just at compile time. You need to have like guarantee, yes, this is going to be at compile time. This will never actually generate any code at runtime. And so now we have a new keyword for that, which is called const-eval. We have lots of new keywords in C++ that start with the letter CO. We had 5 of them in C++ 17. Now we have 11, right? Because you also have CO underscore. I'm not going to talk about that. But anyway, const-eval, that's great. The first proposal for this was to spell it like Const Expert exclamation mark, like really Const Expert. The committee didn't like the exclamation mark thing, so we ended up with const-eval. So that says it has to be at compile time. If it's not a compile time thing, then it's going to give you an error, right? This is great. Except we are still not done yet. So we have the stuff compile time, runtime. Now we can say this has to be compile time. But sometimes you want to do something else. Sometimes you want to kind of overload in a way on whether it's compile time or runtime. And that's something that is not possible in C++ 17 either. So sometimes you have one way of doing things at compile time and another way of doing it at runtime. And you want to do both, right? So let's look at an example. Let's say we have the square function, right? So at compile time, it will just do I times I, all right? This is obviously possible at compile time. But maybe at runtime, you have a special fast way of doing this. Like we have some special CPU instruction which will compute the square a lot faster than this expression. Okay, this is made up, but for other things like inverse square root or like fused multiply add or stuff like that, this is actually a thing. So you might not want to use the Const Expert version at runtime. At runtime, there might be another way of writing this which is faster for performance. So now you write this, but now it can't be Const Expert anymore, right? Because this is a special instruction. So what do you do? So you can make it Const Expert again, but then you can't write the special instruction. So in C++ 20, you can branch on this. So you have this new function called std_constant_evaluated. And that's going to be true if you're evaluating this function at compile time. It's going to be false if you're evaluating it at runtime. And now you can have these two branches. So you can say, well, okay, if I'm in Const Expert land, then do this. And if I'm at runtime, do the fast thing. And the beautiful thing about this is that this condition is going to be evaluated at compile time. So it's going to take the first branch for all the compile time stuff where you use this function. And then it's going to know that from then on, okay, now your code is actually running. So from then on, it will be false. So it's going to optimize this whole branch out, and you're left with just a runtime version. So it never adds any runtime overhead. Good question. Should it be if Const Expert? Well, what would happen if it would be if Const Expert? If Const Expert is evaluated always at compile time, right? Because if Const Expert is a compile time thing. So if you would write if Const Expert still is constant evaluated, it will always be true, right? So that's not useful. So this is why it has to be an if at runtime. If you write if Const Expert is constant evaluated, it will always be true. You will never get the other branch. So it has to be if that is constant evaluated. Does that make sense? This is a tricky bit about this. Yeah, you never write if Const Expert. I think compilers gives you actually warning about this, that this is an error. All right, I think 5 minutes left. I have a few last-minute little additions here. So one thing here is, what's wrong with this code? Is this going to compile? Container is const? Yes, it is. That's weird. Yes, thank you. Container const iterator.
You use the word type name for container iterator on the right one?
Yes. So this is really weird because the compiler already knows that this is a type name because it's a training return type, so it can only be a type. But because of the annoying rules of the language, it says, well, you just have to write type name. In CS20, you don't have to write type name. And actually, yes, const iterator. So I fixed it on this slide. For some reason, I didn't fix it on the previous slide. Sorry for that. Yes, it has to be const iterator. All right. We have a bunch of new attributes. So you have likely and unlikely. You can give the optimizer a hint, like for the branch predictor, which branch is more likely. Have to be a bit careful with that. Look at the actual assembly. Sometimes the generated code is actually worse. Be careful with that. No unique address is really cool. So you know how if you inherit from an empty class, it's not going to take any storage. But if you have an empty member, it does, because it says every member needs to have a different address. So even if it's an empty struct, it will still be like consume a byte. If you put this attribute on it, it won't. So that's great. It saves memory. We can put no discard on constructors. You can have a message in a no discard. Last one, no, actually, you have two more. One is this. So enum class, right, is great. It's better than enum. It's safer. But with the enum class, you need to spell the enum name, right? So if you use it, then you have to always say this kind of enum class name, : enum constant. And sometimes this becomes really long, and people say, I don't want to type all this stuff. So, and then what they do is they say, well, this is too much typing. I'm going to use the old enum instead. This is obviously the wrong thing to do, but this is what people are doing. This makes me sad. But in C++20, you can write using enum name, and then you don't have to type it. Great. And you can actually even do this at class scope, right? So this works like using namespace. If you think of an enum as a namespace with a bunch of integer constants in it, then this would be the equivalent of using namespace, right? So it's something like this. So you can use using enum, and then you're going to pull all the enum constant names into this class. And then the very last one is this. So you know how we have UTF-8 literals in C++? And in C++17, you can use this, right? You can write a UTF-8 literal, and you can assign it to a const char. This is going to compile, because a char star can alias any other type, so that's allowed. But what does it do? What does it mean? Char star is not UTF-8, it's char star. So if your system encoding happens to be UTF-8, it will do the right thing, probably, but for example, on Windows, your system encoding will definitely not be UTF-8. So this is going to contain some garbage, and basically this is useless. So in C++20, this is going to be a compiler error, which is good. And we have another type, a new fundamental type, which is char_8, char8_t. And that's going to be an actual UTF-8 char literal. And that's going to do the expected thing. That's going to hold the correct literal in it. There's a lot of stuff around it as well in the standard libraries. Now you have std_u8 string, which uses this, and std_u8 string view, and all these things. So you can actually now program with UTF-8 strings in a sane way. The only thing we still don't have is I/O streams for these things. So you'd have still no way of getting any of these strings into your program or out of your program. I hope you're going to fix that soon, but in the meantime, as long as you're within your program, this works. So this is great. So this is all I have. This is, again, the schedule. So we have one more meeting here, which is just going to fix some last-minute bugs, most of which we already fixed in Belfast. And then after this meeting, there's going to be a new standard. And then you can get to use all these new things. So that's all I have. Thank you for listening. Yeah. And I think we have these ducks and T-shirts here. So I'm not sure how this works. I guess everyone who asks an interesting question gets a duck or a T-shirt, right?
Спасибо за доклад. В общем, я на русском спрошу, чтобы побыстрее было.
Да.
Вот страница 57, там где decal type от лямбды.
Да.
Вообще, насколько я знаю, каждый инстанс лямбды может порождать новый тип, и как это работает, если мы используем decal type. Вот. на чем-то таком, а потом мы используем это как бы уже с настоящей лямбдой, и какие там будут в итоге типы. В итоге у всех лямбд, у которых нет capture, у них одинаковый тип или…
Это интересно. Я, кстати, вот смотрел на это как раз недавно, потому что у меня тоже возник такой же вопрос. Значит, если вы пишете несколько разных лямбд, то у них будут разные типы.
Да.
Но если мы напишем одну лямбду и потом скажем, например, какая-то там auto-лямбда равно там какая-то лямбда expression, и потом делаем decal type этой лямбды новая лямбда, то она будет иметь тот же тип, как первая. Так
Да,
что теперь можно иметь несколько лямбд, которые имеют одинаковый тип.
Да, это всегда работало. Ну, то есть вот здесь в декларации будет какой-то у них общий такой тип, общий для всех.
Да, значит, у всех
лямбд
этих
так.
лямбд, которые вот здесь внутри будут, у них будет одинаковый тип.
Окей.
И даже обычно, вот, например, имплементация unique pointer такая, что даже инстанс будет один. Так что даже объект лямбды, он будет один между всеми версиями этого unique pointer.
Второй вопрос был насчет класс template argument deduction. Мы когда-нибудь его получим для, например, передачи в функцию, чтобы мы могли сказать то, что у нас функция принимает какой-то там вектор, std-вектор, пробел век, и не говорить, что это там template type name t.
Это у нас не работает. Это, наверное, дискуссия, которая снова придется об этом говорить для C++ 23. Проблема, значит, была в том, что если мы пишем std-вектор как параметр и не пишем template-аргументы, то мы этим превращаем функцию в шаблон, но это никак не видно в синтаксе, что это не функция, а шаблон. И это проблема, потому что шаблоны, они имеют другие свойства, чем функции, поэтому нужно, чтобы всегда было видно, что это шаблон. Поэтому если у нас auto-x, то это видно, что это шаблон. А если у нас просто какой-то type name x, то непонятно, это шаблон, это CTAD или это просто функция. И поэтому вот это…
Ну, теперь
значит,
с авто в декларации можно будет сказать авто std-вектор век.
можно,
Ну,
но
как
тогда, значит, получается такой странный конфликт с концептами, потому что они тоже пользуются тем же синтаксом. Так что непонятно, это CTAD или концепт. Так что вот с таким синтаксом это, наверное, не получится, и поэтому у нас сейчас в стандарте этого нету. Нужно придумать какой-то другой синтакс, наверное, для этого.
Спасибо большое.
И, наверное, можно взять уточку или футболочку.
Еще раз спасибо за доклад. Такой вопрос. Вот теперь мы можем копировать лямбды,
Да.
которые не имеют кэпчеринга.
Да.
То есть появится ли когда-нибудь возможность скопировать лямбду, у которой есть какой-то кэпчер? Например, я засунул в лямбду какое-нибудь там значение, с которым сравниваю, отдаю это в другой поток, и там хочу с этим что-то делать. Вот. В GCC, правда, такое работает, если на свой сторож копировать. Clang не хочет. Хочется, чтобы это было вообще в стандарте.
Ну, звучит нормальная, хорошая идея. Напишите пропозал.
Спасибо.
Это всегда стандартный ответ, если кто-то говорит, а нельзя ли сделать вот эту крутую фичу и иметь ее в стандарте, то ответ всегда один. Пишите пропозал, приезжайте, и, значит, тогда это можно будет сделать.
Спасибо за толк. У меня вопрос по non-type template аргументам. И конкретно по как работают даблы, потому что, насколько я понял, в последнем митинге что-то поменяли, но до последнего митинга там нужна была гарантия, типа strong equality гарантия,
Да.
или как она называлась? Типа,
Да,
как мы сравниваем даблы вообще, чтобы…
Да, у дабла этого нету, потому что там есть not a number.
Как мы делаем, например, темплейт от not a number или там от infinity, например? Как они…
Ну, мы не делаем floating point comparison, потому что floating point comparison для этого не работает. Мы делаем, в принципе, мы сравняем значения. У нас уже такое есть, например, если есть stud atomic float, и потом делать, например, compare exchange, то он делает bitwise comparison. Так что да, нужно с этим быть осторожно. Да, с этим нужно быть осторожно.
Такой вопрос, спасибо за доклад. Такой вопрос. Почему не упомянули передачу строки как template value argument?
Почему?
Передача строки как
Да.
template value argument. Не как тип, а как value.
Передача строки как non-type template argument. Значит, с строкой, стандартной строкой это делать нельзя, потому что у нее есть private members, и там, ну, она не соответствует вот этой вот новому structural type. Но C++ 20 позволяет написать класс fixed string или там compile time string, позволяет написать строку, которая будет работать как non-type template argument. Так что это возможно. Нужно просто в библиотеке этого типа compile time string для этого пока нету, но значит, новые правила позволяют его написать.
То есть
так что в принципе это работает
в
сейчас.
библиотеке compile time regular expression так и сделано.
Да, там так сделано. И это можно самому написать. И я думаю, что в следующем стандарте у нас будет какой-то stud fixed string именно вот для этого. Но сам механизм уже работает.
Вопрос?
Мне кажется, что у нас кончилось время, да? Так что давайте тогда дальнейшие вопросы можно обсудить. Просто вот, ну, приходите и давайте будем общаться. Спасибо.